Great. So thank you to the organizers for having me. I've had a lot of fun so far. It's fun to see so many familiar faces and meet some new people. So I'm just going to jump right into it. So observed dwarfs exhibit diverse rotation curves at fixed Vmax. And this is very nicely presented in this paper by Isabel Santos. So CDM, or NFW, predicts that for a fixed halo mass, or Vmax, which is a proxy for halo mass, that you get identical rotation curves. And so this is what's shown in black with a gray shaded region. So that's the NFW prediction. This is a set of galaxies from the SPARC survey with a similar mass. And what you see in the data is something different than this prediction. So for example, in this upper left-hand panel, you see in the data, so the red, that you have something that's more steeply rising than NFW in the central region. These two center panels are more similar to the NFW, or cold dark matter only prediction. And this lower right panel is showing something that's more slowly rising in the central region than the NFW prediction. And so people have worked to quantify this diversity in rotation curves. Initially in Omen, it was looked at 2 kpc, but in the Santos paper, which is the definition that I'm going to use, is this fiducial radius, which is Vmax by 35 kilometers per second, and a corresponding fiducial velocity, which is the circular velocity at this radius. And so this is just a way to look at the central velocity, which you can see RFID denoted here, the central velocity of these rotation curves independent of the mass scale. And so Isabel shows this for a number of observations, so not only for SPARC, but things and little things. So this is the central velocity, Vfid, on the y-axis, as a function of Vmax on the x-axis. The NFW prediction is this black line with the gray shaded regions, denoting 1 and 2 sigma for the scatter and the mass concentration relationship. And this dashed line is the 1-to-1. Now this is colored by what Isabel calls eta rot, which is Vfid by Vmax. So it's a proxy for how fast or slow the rotation curve rises in the central region. So things that are blue here are more slowly rising than NFW, and things that are more yellow are rising more steeply than NFW. And you see that at a fixed Vmax, you have a large spread. So this is this diversity problem in this Vfid versus Vmax. Okay. So there have been a number of solutions to this problem proposed in the literature, and I will go through 3 of them. So the first case is if you have cold dark matter with baryons. And to get some intuition for this, I'm showing a dark matter density profile here. And people look at the slope of the central dark matter density profile and have shown that feedback can affect what this slope looks like. So the dark matter only prediction is shown in these black X's, and this is consistent with a slope of negative 1.5, independent of the mass scale. But once you include baryons, what happens is this slope changes depending on if you're getting a more chord-like profile at bright dwarfs compared to something that's more chord where you're at classical or the ultra-faint end. And the scatter in this slope will translate to differences in how fast or slow the rotation curve rises in the central region. So that's a CDM prediction. Now, the self-interacting dark matter prediction, there are 2 different cases. And I'm actually just going to start by talking a little bit about what happens with the self-interaction, although Robin nicely primed me, so I don't have to go into too much detail. So there are sort of 2 phases. There's a core phase, and then there's a core collapse phase. I'm actually going to start with this upper right-hand panel. So this is velocity dispersion as a function of radius, colored by look-back time. So this purple curve is the earliest time. And so what you see is, as Robin was saying, the self-interactions basically just give a way for the dark matter to exchange energy. So what happens is at early times you have, so the velocity dispersion is a proxy for temperature. So at early times you have a hot outer halo and a cool inner halo. And the self-interactions, they give you a way to exchange energy, and they try to bring the distribution into thermal equilibrium, driving the density from something that's cuspy to something that's closer to isothermal. So this is the core phase. The second phase is this core collapse phase, where you, because you're a virialized system, get a negative heat capacity and eventually drive this gravel thermal collapse phase. Okay? So how fast this happens has been parameterized in terms of the self-interacting dark matter cross-section, M200 and C200. So at a fixed mass and thus cross-section, there's some scatter in the mass concentration relationship. So at a fixed M200, you will get some halos that are in the core phase and some that are in the core collapse phase. And this will translate into a difference in the how fast or slow you rotate in the central region. And the second case, which Robin also alluded to, was presented in Ren et al. And as Robin said, the self-interactions basically tie together the baryonic and the dark matter components. And so what happens is, they fit these profiles with surface brightness profiles. So this is from the Sparks data. And what they showed was these high surface brightness galaxies, SIDM can't form a core, but you tie the baryons and the dark matter very nicely together. And so you're driving something that's more steeply rising because of the high surface brightness baryonic distribution. Whereas these galaxies that are more slowly rising, in this case, they're low surface brightness, and so they're dark matter dominated. And so SIDM can form a core here. So there are these three different scenarios. So what I have been working to do with my collaborators is to generate a suite that will test all three of these scenarios. So we're working to generate a suite where you, is this not going? Oh no. Oh no. Okay, I don't know, sorry. So the cold dark matter plus baryon case, the case where you have SIDM core expansion, so this is a low cross-section plus baryons, and also the case where you have SIDM core collapse. And so the status is we have 32 of 40, we're aiming for 40, completed in CDM plus baryons. We have 16 of the SIDM core expansion, and I'm still doing some DMO convergence on the SIDM core collapse case. So I won't talk much about that, but you can ask me about it later if you're interested. Okay, so starting with the CDM case, this is again from Santos. This is the observations. But the point is that previous simulations with CDM and baryons have really struggled to produce this diversity in the VFID Vmax plane. So in Apostle, they have a low density threshold for star formation, so they don't produce cores. They're only producing these more steeply rising objects. In Eagle, they have a high density threshold for star formation, and so they are able to produce these more cord-like objects, but not the steeply rising objects. And the same thing happens in Nihao. Below 100 kilometers per second, they're only producing these more cord-like objects. Okay, you can also look at diversity in this size mass plane, which is pointed out by Jiang, I think. So the gray region here is, again, the Sparks data. This blue, so the y-axis is the half-light radius, and the x-axis is the stellar mass. The gray is spark. The blue is late-time galaxies for normal-sized galaxies. So things above this relation are things that are more diffuse, and things below this are objects that are more compact. And the point is that at stellar mass of 10 to the 9 or below, Nihao and Fire are only producing these more diffuse objects. They're not producing any of these compact objects in the Spark data. Okay, so here's a first look at the marvelous Marian zooms in CDM. And I should say this is an extension of the DC Justice League simulation suite. And the point of this is that we're producing a diverse morphology at fixed mass scale. So not only are we producing these diffuse objects, but we're also producing these very compact objects. Okay, so how are we looking in the VFID Vmax plane? So the black points are the CDM zoom simulations, and the green is a Dwarf volume, so dwarfs from a Dwarf volume. And if you look below 100 kilometers per second, you see that we are producing both objects. This is NFW. We're producing both objects that are more slowly rising than NFW and also more steeply rising than NFW. So we started by really trying to simulate galaxies in 70 to 100 kilometers per second. And now we're trying to push down in Vmax to produce galaxies at lower Vmax or halo mass. but we are producing a nice spread compared to previous simulations, so both these compact and diffuse objects. And you can see this also in the size mass plane. So again, Fire and Nihao are only producing these diffuse objects below or at 10 to the 9. And what I'm showing here is same thing. So Spark is in gray. Late time galaxy relationship. So for the normal galaxies, it's in blue. The black is the Marian zooms in CDM, and the green is Marvel. And you can see that we're producing both these diffuse objects as well as some compact objects as well. Okay, so now for the SIDM case. So I said that I was going to consider two different suites. And so the way that I am going to present this is by looking at the cross-section as a function of velocity. So we're looking at velocity-dependent self-interacting dark matter with a UCal-like interaction. So what I have done for the core collapse SIDM case is I use this expression by Zhang, actually, which parameterizes how fast the collapse happens in terms of, again, the cross-section M200 and C200. What I do is I fit core and astro profiles to my CDM simulations and get C200. I get M200, and then I say that I want the collapse to happen by Z equals 0, and that allows me to calculate the cross-section that I need to run these simulations to get core collapse by Z equals 0. And so this is the prediction for my Marian zooms. And so this is the cross-section that we've proposed for the core collapse SIDM suite. So the second case is this, what I'm calling core expansion SIDM. So you're not going to form a core collapse by Z equals 0. And we have chosen to use this purple curve, which is consistent with Ren et al. 2019 in the area where diversity is maximized. Okay, so Ren again showed that they could solve diversity because of the coupling between the dark matter and the baryons, so the way that the self-interactions tie those two things together. And what we see preliminarily, so this is a fit, I should say, this is a fit. And what we see in our core expansion SIDM simulations is the same thing. So we're actually able to produce this in the simulations. So I've taken simulations that are in the CMC max range, and I've colored them by surface brightness. And you can see that there's some relationship between how fast or slow the rotation curve rises and the surface brightness. Not too surprising to me, though. The same thing happens in CDM plus baryons. So you also see a relationship between how fast or slow the rotation curve rises and the surface brightness of the object. Okay, all of this to say that the same mechanism that's giving diversity in this core expansion phase is similar to what's happening in CDM plus baryons. And so we're seeing similar diversity in the core expansion SIDM simulations as we are in the CDM plus baryon simulations. So the circles are now CDM plus baryons with their counterpart in the same color but with a plus. And so we're seeing similar amount of diversity, but if you look at the actual distribution, so this is very preliminary, but if you look at a kernel density estimate, the core expansion SIDM does shift in VFID by Vmax to lower VFID by Vmax slightly. So they are producing similar diversity, but there are some slight differences that we're still exploring. Okay, so the last thing that I want to talk about is this point that was made by Isabel, and I think I've gone way too fast. So I think I have a little time for this. So Ren said, okay, well, it's the surface brightness that is really helping you to get diversity. And what Isabel pointed out is, okay, so this is a complicated plot, so let me piece it apart a little bit. So eta rho, again, is VFID by Vmax, so how fast or slow you rotate in the central region. So this is the NFW prediction. Things below that are rotating more slowly in the central region than NFW, and things above are rising more steeply than NFW in the central region. Now she's colored these points by Vmax, which is a proxy again for the mass of the system. So I'm going to start by thinking to get a little bit of intuition about these yellow points. So those are massive galaxies. They have high Vmax. And so what's happening in this case is that you get baryonic contraction, and so you're getting things that are rising more steeply than NFW in the central region because of that baryonic contraction. These objects over here, oh, sorry, I didn't explain the x-axis. So the x-axis is the VFID of the baryons in the fiducial radius, divided by the total fiducial velocity squared. So this is basically a proxy for the baryonic mass fraction within VFID. So think GM over R, assuming spherical symmetry. So again, these objects have high baryonic mass fractions, and they're also massive galaxies, so they're more steeply rising because of the baryonic contraction. These things, however, over here, have low baryonic mass fractions, but they're rising more steeply than NFW. And previous simulations, again, really struggled to reproduce these objects. So these steeply rising rotation curves with low central baryon mass are challenging to the CDM plus baryon picture. So now I'm showing the same thing with my CDM plus baryon simulations. So this is the spark data, again colored by Vmax on the left. On the right, I'm showing spark in gray, and I'm showing my simulations, again colored by Vmax. And what you see is for the region where I'm producing the simulations, I am able to produce these objects that are more steeply rising than NFW, but have low baryonic mass fractions. Okay, so diverse dwarf galaxies exhibit diverse rotation curves, and the marvelous dwarf simulations with CDM and baryons are able to produce this diversity in multiple planes. The core expansion SIDM with baryons produce similar diversity in the VFID Vmax plane, but there are some differences that we're still exploring, which may be related to Robin's earlier comments. And these steeply rising rotation curves with low central baryon mass fractions, I should say, motivate core collapse SIDM, which is also something that we're exploring, but still doing some numerical convergence testing on. And then I just want to say thank you to my collaborators and, again, the organizers. Thank you.